happy to be here. Can you hear me? Nobody answers. Yes. Okay, good. So thank you very much. Just arriving here in this school in Paris feels like a privilege for me. So I'm grateful to Cyril for this initiative and for the organization. As Cyril said, there are two speakers in this school. Joseph speaks in the afternoons, and I do the mornings. And the division, more or less, is that Joseph will discuss things that are related to stochastic processes, and more or less I do things that are other stuff, like things that are not completely directly related to stochastic processes. Now, if something is not clear during my lecture, I understand it's not completely trivial to ask questions, but if I can speak loud and everybody hears, maybe there is some symmetry. There is some symmetry. Maybe you can also try, if you have loud voice, to ask questions, because I really enjoy it when the audience is active. I think, from my experience, it's better for everyone. And I would say the acoustic is good enough not to use the microphone, no, maybe, for questions? Let's try. So, for sure, the first rows may stop me and ask questions whenever you want. This is completely recommended. Okay, now, at least my plan for these 4 days is described in the lecture notes. The lecture notes are available at the school website and also through my homepage. So if you go to my homepage, teaching, then the first link should be the lecture notes. Okay, so we're going to begin with the Poincaré inequality. Not because of the HP, just because that's what we want to begin. So this is an inequality that was proven by Poincaré in the years 1892, 1896, 2 papers. So we have a measure mu, which is absolute continuous probability measure in Rn. The density is rho. And we assume that the density is low concave. So this means that if you take any convex combination of 2 points, so for any 2 points in Rn and any lambda, if you take the convex combination of 2 points, the value of rho the combination is larger than the geometric average at the endpoints. Okay, so this is a local absolute continuous probability measure. The main examples are Gaussians. So any Gaussian, let's say of absolute continuous Gaussian in Rn is low concave. And also, if you take uniform distribution in a convex set, so if K is convex and rho is the indicator of K, maybe proportional to indicator of K, then it's okay, because 2 points inside it's fine. So these are the 2 main examples for low concave measures. Also, let's say that we allow measures that are supported on a subspace. So if mu, so we say that mu is low concave, also if it is supported in a subspace, and absolute continuous in this subspace, with a local density is there. So this is fine for us. So a low concave measure again, if it is supported in a subspace, and there it's absolutely continuous, a fine subspace, and then the low concave there, this is again called low concave. Okay, so what is the Poincaré inequality? So let's say that we have a convex set K in Rn. Mu low concave supported in K. Let's say bounded, otherwise it doesn't make much sense. Supported in K. And f is some function on, well, only here, of course. C1 smooth function, integral 0. Then what Poincaré proved is that the L2 norm of f with respect to mu is at most some number. So the Poincaré constant times the integral of the gradient of f And under these assumptions, what he showed is that, okay, actually proved it only for uniform measurement convex sets, not for all concave, but okay, it's not that different. But the Poincaré constant, it moves some dimensional constant times the square of the diameter of K. So Cn, okay, well, actually it does not, well, a posteriori we know it does not depend on n, but at least, so this is depends only on n, at least for now, on the dimension, and the diameter is the, you know, okay. Okay, so this is the Poincaré inequality. So the idea too high, no? Descente. Okay. Arrête. Okay. Okay. Yeah, okay, so this is the Poincaré inequality. So if you've never seen it, so what you can see is that if you know that the gradient of f is small in some average sense, so it means that locally the function does not fluctuate too much, then it implies that the function on a global scale does not fluctuate too much. It has small variance. The integral of f is 0, so the L to norm of f is the variance of f roughly. Okay, and just two remarks. So the best, so I wrote Cp of mu. So best constant in the inequality for mu. So Cp mu is the best constant. In the inequality for mu. Okay, it's called the Poincaré constant. And second remark is that in the 60s, so this is from 19th century, in the 60s, Penn-Weinberger found the best constant Cn. And in fact, it does not depend on dimension. So Cn, the best one, is 1 over pi squared for any n. So it's nice that the optimal constant does not depend on the dimension. Okay. Now, actually, if you look on, okay, I'll discuss the applications later, but I would say that for applications in fixed dimension, pretty much Poincaré is enough. And for high dimension, you need something closer to KLS. But still, it's good to know the dimensional constant. Questions about this inequality? Maybe someone speaks and they cannot hear you because no microphone? It's not the case? Yes. Yes, please.
I'm a bit confused by the hypothesis with
Which hypothesis?
the support of mu is contained in a finite surface.
Ah, okay.
So I can only take RD surface, so will this play a role afterwards?
Sorry?
Will this basically play a role afterwards?
Not so much. Let me just write you a careful definition so that there would be no question. So I would say that a probability measure mu in Rn is low concave, or a measure, not probability measure, mu is in Rn is low concave. If there is some subspace, if there exists a fine subspace E, so that support of mu is E, so that mu is supported in E and absolutely continuous there. Absolutely continuous with the density in E with density rho satisfying this inequality, satisfying the above. So that's the completely accurate definition of low concave measure. So, and the good thing is that now, for instance, all Gaussians are low concave, including Gaussians that are supported in some line in Rn. So if you have or delta measures. So again, according to this formal definition, these are also low-concave. So we're going to pass to a subspace and have your support there and still call it low-concave. That's a good class because it's closed under weak limits. Okay, so one property of one consequence of Poincaré inequality is that if you take a weak limit of such measures, it's again a low-concave measure. That's why it makes sense to consider this class. But usually we just have support in all of Rn. We would not have this. This is just to be fully accurate.
Okay, thank you.
Yes?
If you have to upload the variance of this function, what will be the optimal bound? Because this is modeling the variance, right? You got the variance of the function based on average of the value.
Mm-hmm.
What is the optimal bound?
This is the case conjecture that will be discussed shortly. That's some bound. Okay, so let me proceed with an adaptation of Poincaré's proof. So that's this does not use sophisticated tools, relatively sophisticated from the 20th century. The idea is as follows. So we begin with a function f. Okay, so the L2 norm of f. Well, that's, as I said, I don't know, it's also the variance of f because, meaning the integral of f square minus integral of so. Okay, it's the variance of f. The variance of f is the integral of f minus e square, where e is the integral of f d mu over mu of k, is the average of the function f. Okay, because the Lagrange is 0. And now we can rewrite the variance as follows. So we have our domain k, and we can look on all pairs of points x and y, and you know there is a way to write the variance as use a probability measure or not? Did I assume it? Let's assume it's probability. It's not important. So let's assume that mu is a probability measure. Okay, and then I don't. Okay, so in this case I can write the variance as f of x minus f of y square d mu x d mu y. Right? That's the average. If you open the brackets, it's the variance. And now the idea is to use the fact that we have some convexity condition. We are in a convex set. We are a low-concave measure. So we connect x to y by a segment. Right? That's the important property of convex sets. And we look at the difference, f of x minus f of y, and we express it as the integral of the derivative of the function along this interval, right? So f of x, we write f of x minus f of y as the integral from 0 to 1 as the derivative of f of 1 minus tx plus t of y dt. That's the, no, f of y minus f of x here. Okay, so when we proceed as follows, we can write that this equals half of the double integral, and here I have the integral from 0 to 1, and by the chain rule, I'll get this in. Okay. Now we will use the bound on the diameter. So we know that x minus y is at most the diameter. So it says that this is at most the square of the diameter times, and let's do a Cauchy-Schwarz also. So why not? Okay. So dt, and I'll use the density rho x rho y dt dx dy. Okay. Now, what do you want to prove? So we have some expression for the gradient of f, okay? But it's not exactly the expressions that we want in the inequality. So we just need to manipulate a little bit, okay? So our goal is to show that for any t between 0 and 1, the inner integral inside the integral over x and y. So we want to have this expression and integral w cut over k times some coefficient depending on n and on t. So if you have it for any t, we can integrate on t and get this bound. Okay, so what can you do? Well, the idea is now to use low concavity. So if you look at rho of x, rho of y, somehow what you would like to do is to replace it somehow by some expression of this sort, and then change variables. So if you have this thing, you can call it a new variable, and you get something like this integral. That's the idea. And for this, you'd use low concavity. This is not completely true for the general measures, but and low concavity, it's OK. So what does low concavity tells us? Low concavity tells us that, by definition, that if I look at rho at this point, it is at least the geometric average of rho at the endpoints. And I'll use something even simpler now. I'll use the fact that it's at least the minimum of the values at the endpoints. OK. And now, what will I do with this product? I need to upper bound this product by something involving this thing. So I'm going to say the following. I'm going to say the product of two numbers is the maximum times the minimum of the numbers. OK? So I'm going to do nothing with the maximum, but I'm going to replace the minimum by this expression here. And then the maximum will be replaced by the sum. OK. So what do we get with this? What can we say about this expression? Now we get the following. So this will be used for some region of some region of t. So now star, the inequality, at least the expression on the left-hand side here, is at most. So grad f at some point. And then I'm going to have rho at. So this is the things that I would really like to have. And this would just, OK, this would stay there, at least for now. OK, and now we split into two integrals, this expression and this expression. And I'm going to change variables. So u would be 1 minus tx plus ty. OK, so let's first look at the first integral. So it's going to be, I'm going to have integral du dx. Yeah. And what would be the Jacobian? So x is fixed and it's a function of y. So du is t to the n dy. So I need to divide by t to the n here. And I'm going to get grad f at the point u square rho of u rho of x. And for the other term, it's going to be pretty much the same. So here it will be du dy. So I'm changing, y is fixed. I'm changing x to u. And du is 1 minus t to the n. I mean, the integral is 1 minus t to the n to dx. And you need to divide by 1 minus t to the n. So we get, OK, and the integral over rho y, since the probability measure, the integral is 1, and this just equals 1 over t to the n plus 1 over 1 minus t to the n times what we wanted. Okay, now this is good if t is roughly 1/2, say. But if t is close to 0 or to 1, this explodes. It's not such a good idea. And for t which is far from 1/2, we'll use another bound. No. This one. So there are, all we use so far is that the density is low concave. From low concavity is the fact that the value at the convex combination is at least the minimum of the value of the endpoints. Now we use, for t which is close to 0 to 1, we'll use another little fact from low concavity. So for t which is, for t, let's say, okay, close to 0 to 1, so what will we do? We'll change variables a bit differently in a way which is maybe more uses low concavity. So what can we say about this expression 1 is tx plus ty times what we get if we switch x and y? So if we switch x and y, then in the convex combination, we're going to get complementary numbers. So first we get lambda and 1 minus lambda, so that's sum to 1. So this is what low concavity gives us if you have look at two numbers like that. Okay, so the average, if this is 0 and 1, and you look at the values, this time this is larger than this times this in the low concave case. And this seems sound like more, okay, so let's see what do we get when we use this bound for the Poincaré expression. Then we get that, so we'll get grad f at one of them, I think the one with x. And then rho at convex combination of 1 minus tx plus ty times the other combination, 1 minus ty plus tx dx dy. And here the change of variables should be a bit more symmetric, so u will be 1 minus tx plus ty, and v will be 1 minus ty plus tx. Okay? And just note that if t equals 1/2, this makes no sense at all, because for t equals 1/2, u equals v, so it's not a reasonable chain of variables. But if t is far from 1/2, it's going to be good for us. And now what's going to be the Jacobian? Okay, so this should be, this equals grad f, I think this is u. Yeah, this is u square. Rho of u, rho of v, which is, and then du dv, and I put here some space because there should be some Jacobian. How do you compute the Jacobian? Okay, I do it with differential forms. So let's look at the j's coordinate. So if I look at duj wedge dvj, then this should be dxj. And uj would give us y minus tx dy, so y minus t square. And this term, ty tx, will give us t square, but with a minus sign, going to be with dy wedge dx. So minus t square. So, and this means that if you do it n times, I'm going to get this thing to the n. And this is density in no differential form, so it's absolute value. So square minus t square to the n. Okay, and this equals 1 over 1 minus t square to the n times the integral of grad f squared d mu. Very good. So we have two bounds for this expression. Each of them gives, on the right-hand side, the L2 norm of the gradient. That's what we wanted. And we have two choices. We can choose which, according to t, we can choose which bound we would like to have. OK. So let's complete the proof. Okay, so to summarize, what we got is that the L2 norm of F is smaller than what? So there was some 1/2, and then there was, okay, this term. And then there is the integral from 0 to 1 of the bounds for each t. And the bound for each t we can choose. So we can choose between one, I think this was one of the bounds. Wait, this is the third table should go. Okay, this was one of the bounds. And the other one was this to the n. Now, let's look at this expression. So this is now an integral that we should estimate to some extent. There are two different regimes. So if t is close to 1/2, so if t is between half minus 1 over n and half plus 1 over n, in this case, these two things are too close to each other, and we might divide by 0, so we don't want that. In this case, we take this bound, and this would give us 2 to the n times some constant. So in this case, this would give the first terms dominate, and it is at most 2 to the n, the integrand, okay? And if t is outside this interval, then one of them is at least twice the other term, and we have the integral of, we get something like the integral from 0 to 1 of 1 over t to the 2n or something, which is to the 1/2, which is at most it's 1 over 2n plus 1, 1/2 to the 2n. So all in all, what we get is that this thing is at most 2 to the n over n times c, where c is some universal constant. Okay, I didn't quite completely optimize. But I think we proved the Poincaré inequality. Okay, in general, in this lecture, when I write the letter c, it's almost invariably some universal constant, so the value may change from one line to the next. Okay, questions? Okay. Okay, so this is the Poincaré inequality. Okay, now let me tell you some things about the geometric meaning of the Poincaré constant. Let us consider the case. So suppose that mu is uniform in some domain K. In some domain K in Rn. In this case, well, we write Cp of K sometimes. So Cp of K is Cp of mu, just, okay. And let's look at two cases. Yes, please, please.
So can you explain maybe why, like, in an idea it's problematic to be half?
Yeah, it is just.
Not from the proof.
So you want to do a change of variables. So you have, you had this. Okay, first of all, the proof of Poincaré uses the most elementary property of convexity, that you can connect 2 points by a segment. Okay, and then in a sense, you don't get an average of the gradient with respect to the original measure that you want, but you get an average of it with respect to some convolution, right? You get some 1 minus tx plus ty. And you want to bound this, so basically the measure is not uniform in the convex set anymore, but it's kind of some convolution of this with some coefficient. So it's more peaked towards the center. In fact, it is indeed peaked exponentially. It was that if you take 2 Euclidean balls and convolve them, the measure inside is much, much higher, 2 to the n higher. So there is no, once you do this step, I mean, you lose exponential factor in dimension. No way back. Now, okay, now you need to have some tricks to bound this density of the convolution. You want to bound it. So suppose these are random vectors, independent. You want to bound this density by just x, density of x. So you can do some tricks. For instance, and here, for instance, you could have one natural trick is to look at the other combination and see that both together kind of balance each other. And this works okay unless you are at 1/2, because at 1/2 there is no other thing. I mean, change of variables that we like is like x plus y, xy goes to x plus y, x minus y is a good one, or 1/3, 2/3 is a good one. So these are, it means that you change your axis in some incontrollable way. I don't know, 30 degrees, 40 degrees. But if you do something like, if this is too close to 1, it means that you degenerate, your coordinate change is going to degenerate. So it's not a useful thing. And then for this region, if it is very close to 1/2, you do some other trick. You find some way to bound it. You don't change variables. You bound it by something else, and the other thing is okay. Okay, but these are just tricks, elementary tricks using the definition of low concavity. So these just show how it is a handy condition, low concavities that could help you you can use and exploit in various situations. So that's the Poincaré proof. In fixed dimension, it's pretty much okay to use these things, unless you want best constants. But in high dimension, you're going to argue completely differently. More questions? Yes, please. Beatrice, hi. Yes. They used so their proof is the first written text about localization, like hyperplane bisection. They didn't do it completely accurate, but yes. So their idea is to. So tomorrow we discuss. Okay, the plan of the lecture is that tomorrow we're going to discuss convex localization. But their idea was not to just take random x and y and connect them, but to pretty much carefully divide your set K into intervals, to have some partition in a smart way, such that the average of f is 0 on each of the segments. And then it suffices to prove the Poincaré inequality separately on each segment. And then you're in a one-dimensional situation, so there could not possibly be any dependence on the dimension. And then to get the 1 over pi square, you argue differently in one dimension. There is some nice argument. In one dimension, I mean, normal boundary condition and Dirichlet are pretty much the same. The spectrum is the same for the two. I mean, things are much easier. You have little tricks, integration by parts that do it in one dimension. That's their idea. So first reduce it to one dimension, and then find the best one in one dimension. More questions? Yes, so I wanted to tell you what's the geometric meaning of the Poincaré constant. By the way, if I don't know, maybe there are in this audience people that read French, I don't know. There is a nice paper by Aller called on Poincaré inequality with a funny name, like a take on Proust à la recherche de l'inégalité perdue, something like that. If you want, then that's a fun paper about the history of the Poincaré inequality. Okay. Okay, the geometric meaning of the Poincaré constant. So let's look at two examples. K would not be convex. Suppose that K is, let's say, a dumbbell like this. So what happens if K looks like this? Can you say that the variance of a function is bounded by the gradient? Not so much. We can have a function f that equals 0 here, let's say minus 1 here, and plus 1 here. Suppose the average is 0, and there is a small bottleneck, very small bottleneck in which it has some gradient. So the gradient is basically 0 most of the time. In this little bridge, it does something, goes from minus 1 to plus 1. But then, other than that, the integral is rather 0, although the variance is 1. So here you can have variance, which is roughly 1. But the integral of grad f squared could be arbitrarily small. I don't know, let me write smaller than some epsilon. So here you cannot have bound on the global fluctuation from the local fluctuation, because you have this bottleneck. Now, if K is convex, so we know that from the Poincaré inequalities that this cannot happen. So convexity, rules out bottlenecks. at least in button X, at least you see that at least intuitively in fixed dimension. And the question is, so is it also true in high dimensions? Is convexity enough for ruling out button X also in high dimension? Okay, it's not entirely trivial because, and there are applications for which you need to know high dimension. It's not really trivial because we don't have a very good grasp of the convexity condition in high dimensions. I mean, it's pretty common to, we know that there is this concentration of measure effect in high dimensions. In some sense, convex sets look like they have some kind of tentacles in a bit because the mass is located close to some region. So it's not obvious that it should be enough for a good Poincaré inequality, but there is a conjecture which is still not proven. So this goes. This is the first board, and it should go up if you want to press. This is the second board? Ah. Yeah, it's the second. Sorry. Okay. And the conjecture in this business is the Kannan Lovasz Simonovits conjecture. There is some accent in Lovasz, I think here. Do you know? Yeah? So their conjecture is that for any low concave probability measure mu, you can assume absolute continuous. It's not a big deal. It's OK. The Poincaré constant, so there is a simple bound, which I will explain in a second, but it's indeed simple. The operator norm of the covariance matrix. And their conjecture is that up to some universal constant, it is also upper bounded. This thing where C is a universal constant. And this is the operator norm, the L2 operator norm. And the covariance matrix, what is it? So the covariance okay, so this is a matrix, symmetric matrix, n by n. And its ij entry is the correlation between xi and xj. And better actually to switch to probabilistic notation. So let's assume that x is a random vector in Rn, whose distribution law is the measure mu. Okay? So x is a random vector. It's the same information as mu. Okay, so, I mean, we can write, whenever I write CP of x, I mean CP of mu, and whenever I write covariance of x, I mean covariance of u. It's the same mathematical object, just expressed slightly differently. So this is, in this notation, it is the expectation of xi xj minus xi xj, which is indeed the covariance of these two random variables, which are possibly dependent. Okay, so this is the covariance, and the operator norm is just and the operator norm or of x I could write if I want. So this is symmetric matrix, so the operator norm is the super over the unit sphere. This is the unit sphere. And maybe I never said that, but these two bars mean Euclidean norm for me. I don't put two bars. This is this norm. OK, so it's more of covariance of x theta some theta. Or if you want, the supremum of the variance of x times theta. So if you think about it, the scalar product, the covariance x theta is the variance of x times theta, just by bilinearity of the covariance. Yeah. OK, and let me write it as, so let's denote f theta of x to be x times theta, or x. I use these two notations interchangeably, the dot and Klartag product. OK, now what about, so I said that this is a trivial inequality. Let's prove it. So what's the left-hand side inequality? Why is it an easy thing? Because in this probabilistic notation, the Poincaré inequality tells us that for any function f, the variance of f of x, the integral of f squared minus this average square, is at most the Poincaré constant of x times the expectation of grad f x squared. That's the Poincaré inequality, just in another notation. So if you just plug a linear function, so for f linear, say f equals f of theta, what do we get? We get that the variance of f theta of x, which is the variance of theta times x, so it is at most the Poincaré constant of x times the expectation of the gradient of f theta. But this is, since theta is unit vector, this just equals 1. Right? This gradient is just the vector theta, which is unit vector. So we get the Poincaré constant. So the Poincaré constant is larger than the variance. And if you take now the super over theta, so the operator on the super over theta, and you are done. So sup everywhere. Yeah, so you get the Poincaré, at least the supremum, which is the operator norm. OK, so we just test the Poincaré inequality for linear functions. OK, and this is the trivial lower bound for the Poincaré constant, what you get for linear functions. And now, this one. And now, I cannot raise it up, but what the KLS conjecture suggests is that linear functions are all you need, pretty much, up to universal constant. OK, so KLS suggests that Poincaré inequality is almost saturated is essentially means up to universal constant by linear functions. OK, and this is in the low concave case, under low concavity. OK, so the conjecture suggests that indeed, also in higher dimension, there are no bottlenecks hidden. And if you know what happens for linear functions, you know that the variance is not too big, then you pretty much know for all functions. Any nonlinear function would have the same inequality as the linear functions satisfy. OK, so OK, let me write again. So this is the question. Is it true that the Poincaré constant is smaller than a constant times the operator norm? So this is not known yet. What is known is that if you put, so you can put here log n. This is known. Okay, and this is something that we'll discuss in great detail in these lectures. Okay, any questions about the KLS conjecture? Can I? Yes, how to do it? I put this is number 1, up. Okay, so you have a log-cave probability measure, or log-cave random vector, it's the same. So the conjecture is that the Poincaré constant is at most the operator norm of the covariance matrix, up to some factor of 5, universal constant. And what is known is log n. Which is pretty much the subject of these lectures, this log n. Is that it? Maybe you want to ask something? Okay.
Do you expect it to be true?
I don't know. I can tell you what the expert says. I don't know. I'm an expert. Yeah, but also, okay. Let's say Keith Ball wrote that it's too optimistic in Bulletin of the MS a few years ago. But Giannopoulos is more optimistic. Yeah, there are many experts with different opinions about this conjecture. So, also, there are these says that if the problem is hard enough, it's not so important what the experts think because they didn't solve it, so maybe they're not such experts. Okay, yeah, I don't quite know. There is an application which is the slicing. You know that, but I say so. There is the slicing problem which follows from KLS, which I would guess should be okay. But KLS, I'm not sure. I don't have a strong opinion. Okay, so let's discuss a few examples. Okay. Okay, so I want to discuss many examples. Okay, the first example, I would look at the case where x is uniform. So measure mu and random vector x is the same for me. I switch them without noticing. So I have x, always x, mu. This is random vector, law mu. This is the measure, the law, and sometimes I even write rho, which is the density of mu. So I approach this in advance if I'm going to switch between these two things. I'm just used to it. Okay, so the first example, when x is uniform in the interval. X is uniform distribution in some interval, maybe of length L. Okay. So let's test what do we get in this case. The variance, so it's not a covariance, just one dimension. So the variance of x is 1 over 12, L square over 12. And that's easy computation. The Poincaré constant is not completely easy, but if you know to do Fourier series, you would manage. And you get L square over pi square. And that's the extremal case in the proof of Payne-Weinberger. The optimal constant is 1 over pi squared already for the interval. Okay, so we see that 1 over 12 is slightly smaller than 1 over pi squared. 1 over pi squared is 0.1, no? A bit. So, okay. So no contradiction to the fact to this inequality at least. And yeah. So in the uniform margin, it's okay. The extremal function for the Poincaré here, so if the interval is, if L is pi, then the extremal function, it should be a cosine. Is extremal. So if you look at its derivative, the L2 norm of f is the same as the atom of the derivative wave of sign, minus sign, and the constant is 1 as you want. So this is this case. Okay, second example is fx is uniform in a cube. So this time it will be in high dimension. Okay. So what can we say? So the covariance matrix is easy to compute. These are independent random variables. So it will be just 1 over 12 times the identity matrix. Right? I mean, there are no correlations. You're just going to get all the variances. Very good. Now for the Poincaré constant, let me give you an exercise. And this is the fact that if you have, if x is some random vector with independent components, x1 up to xn are independent random variables, then the Poincaré constant, it equals, but let me just prove that it's most the maximum. It actually equals the maximum of this Poincaré, of the small ones. And oh, you can also prove this. Okay, yeah, actually it's easy. Wait, let's prove it. Good. So that's yeah. So the exercise, and if it's indeed correct, you'd get that the Poincaré constant of x would be 1 over pi squared. Okay, so in this case, let me write again. So the covariance matrix, its operator norm, if you want, is 1 over 12. And the Poincaré constant is 1 over pi squared. Okay, so this does not contradict the KLS conjecture. But another thing to notice is that the diameter. Let's see what does the diameter bound gives us. Okay. Now, what is the diameter of the cube, unit cube? Well, the diameter is of course attended the diagonal. The cell length is 1, but the diagonal is root of n. So this is root of n. Okay. So even if you'd use the optimal constant in the Poincaré inequality, in terms of the diameter, you'd get so Poincaré and Weinberger. What they would give you. Actually, Weinberger, what they would give you is a bound which is not that, so some constant times n. This is the diameter square of k. K is 0, 1 to the n. Okay, and this is precisely the, this does not yield any of the, this does not yet, for instance, the fact that the marginals are approximately Gaussian. This is exactly, so if you go below that, you get some non-trivial conclusions, but this is exactly the thing which is not that useful. But now we have, if you believe in the KLS conjecture or use the things that are known, you have much better bound, which is more useful in high dimensions. In fixed dimension, what it is good enough. Third example is the ball. Okay, Euclidean ball and Euclidean unit ball. And x is uniform inside K. Okay. Now, what is the volume of, so the ball is a bit too small in high dimensions, don't you think? It's like the volume is too little. The volume of the ball is a small number. That's, let me brag that I remember the formula. I think I remember. Okay. And that's roughly root of 2 pi e plus little, if you use Stirling's formula, over root of n to the n. So in high dimensions, the unit ball has volume 1 over root of n to the n. It's too little. and it makes sense. It makes sense to scale it. So if you scale it, you normalize the volume, and you also normalize the covariance. You normalize everything, pretty much, Poincaré constant. Okay, so it makes sense. So to normalize the volume or other things, volume or covariance, or whatever. So I look at the ball times. Let's say the new. Okay, this was K. Okay, let me call it T. So T would be the ball times root of n. Root of n is a good thing to put. I put root of n plus 2 just to make it isotropic. But yeah, I put a factor of root of n so that the volume is roughly 1 here. And in this case, so x is uniform in this ball of radius root of n plus 2, okay? And in this case, the diameter is roughly that of, is roughly n, or actually it equals 2 root of n plus 2, but it's roughly root of n up to universal constant. Okay, and the covariance is 1, identity. And the Poincaré constant, so believe me, so it's given by some Bessel functions. It has the order of magnitude of universal constant. So it can be computed. It is some expression involving Bessel functions, but it has the order of magnitude of the right order of magnitude of roughly 1. Okay, so again, the ball is not a counterexample to the Cayley's conjecture. Let me just mention a theorem of Jego and Weinberger. Here, I'll mention it, and then we take a break. Also here, again, if you use the diameter bound, you don't get something, you get a weak bound, but the Cayley's conjecture is much better. So just, so Jego in the 50s, I think. Jego, Weinberger. So the Euclidean ball minimizes the Poincaré constant under volume constraint. I think Jego in dimension 2 and Weinberger in any dimension under volume constraint. So if you look on all domains, not convex, any domain of fixed volume, then it's minimal for the ball. Okay, any questions? So 10 minutes break, Cyril? Okay, 10 minutes? 10 minutes.